Okay, let's continue. So as shown in the example, now it was deleted, that these two uh, trees are the same. So in this case here, the right hand side tree is almost a complete tree, but the simplification that we were able to do was only in this part. Yeah. Then, of course, comparing these other two, then there's any other possible combinations, of course, where you don't start with A as your root node. You can have C as your root node or B as your root node. Yeah. And so the best way to do is just create a full tree and then eliminate some of those that are redundant. Okay. I think that's the way to do it. Okay. Well, in Boolean arithmetic, it's easy because the process, I think most of them are commutative, and so you can just change, the uh, the the nodes, the order of the nodes. In most cases, is not that necessary. Is not that critical. Okay. So, but then the size will change. The size of the tree will change depending on which node you choose. Okay. So anyway, those are much simpler examples. And so if you go to a bigger example, I mean a more complicated example, one is to predict fuel efficiency. For example, in this case, we are, let's now, I'm sharing the screen, right? You can see my screen? Yeah, I think so. So let's go to a more complicated example. In this case, for example, we are looking at a data. Again, always in machine learning, we are given data. Uh, real life, everyday life data. For example, in this case, it's about predicting the miles per gallon or miles per gallon, kilometers per liter if you want, in this case, of a certain vehicle. Yeah. So given the parameters of the vehicle, whether how many cylinders it has, the displacement, the engine displacement, and the horsepower of the engine, and then the weight of the vehicle, acceleration, ability to accelerate, the model the model or the year of the model that it was released, and the maker. Then based on this information, as you can see, all these parameters, cylinder, displacement, horsepower, weight, acceleration, model, and maker, they are all in this as X as the input parameters. And so the Y parameter, the output parameter that we want to know is whether its miles per gallon is good or bad, or just two, good or bad. Okay, based on the input information X that will be given. Now, the problem that we are dealing with in decision trees then is to come out with a function, that this function will define the output good or bad given all the necessary inputs of all these cylinder, displacement, horsepower, weight, acceleration, model, and year. Yeah. So that's the idea. Okay. Previously in the Boolean exercise, we have A and B, or A, B, and C is the inputs, and then it will come out with the result of false or true. Okay, that's the logic. Okay, so for the decision tree, then we need to find a function f with given the input y that will define the relationship of the input y to the of the input x to the output y. This function will define that relationship. So initially, at an overview, we can see that in this case, we can put cylinder as the root attribute, and then cylinder, there's 4, 5, and 6, for example, 4, 5, 6, and 8 cylinders. And then we can make the second layer or the second node as maker and horsepower and so on. Yeah. And see whether we can come out with a good or bad decision. In this case, they're just using 3 parameters, but nothing is hindering us from using all the parameters. Yeah. So for example, if you only use 3 parameters, then this one will be the result. Okay. And then you can build a decision tree out of that. Okay. So in this case here, each internal node tests an attribute xi. So internal node, the internal node in this case maker, and horsepower, you'll have attribute for the maker, America, Asia, and Europe, and then for horsepower, low, medium, and high. So each branch assigned the attribute. So sorry, the this is the attribute, the maker, and the branch is the assignment of that particular attribute. So in this branch, the maker is equal to America. In this branch, the maker is equal to Asia, the country of the maker. And then in this case, or no, not the country, but continent. Uh, in this case, the continent of the maker is Europe. Yeah. So in each leaf, again, leaf is the last layer where you assign a class Y, good or bad. Yeah, depending on the how the tree, the logic of the tree is followed. So to classify the input X, which is all those input parameters Xi, X is consisting of Xi of all those parameters, we transfers to the tree from the root to the leaf and output the label Y. Again, it is defining the function given the relationship of the input X to the output Y. Okay. Learning decision tree is hard, yeah, because they say that this is just a side comment. Uh, for us, we say decision tree is not an easy thing to do because the learning the simplest or smallest decision tree is NA. Please mute your microphone. Who's that talking? The simplest decision tree is an NP complete problem. An NP problem, not an NP problem means non-deterministic polynomial problem. Its solutions are guessed and verified in a polynomial time. So it can be solved by a restricted class of brute force search algorithms. So that means that there's a solution that you can be guessed. There is a polynomial time. That means it doesn't increase, it doesn't increase exponentially or indefinitely. There is a polynomial time that you can find its solution. Okay, so non-deterministic means that there's no rule to be followed to make the guess, but you can make brute force guesses and brute force search algorithms to come out with a solution. So in this case, we will search. Uh, so it is a and it is an empty complete problem where you can find a solution through brute force. So we say that we resort to a greedy heuristic. We start with an empty decision tree and split on the next best attribute or feature, and then recurse, and then we iterate, go through other attributes to find the final decision tree. So that is the method of going through defining or going through the final decision tree by looking at a brute force algorithm. Okay, sorry, can you mute? Who is that? Musa. Musa. You're always the. Can you off your microphone? Okay, thank you. Okay, now let's continue. So splitting. Okay, how do we split? The splitting is when we go to the next branch or you go to the next node and then defining the connection between the branches. Okay, I mean between the nodes through a branch. So we would prefer to split, for example, in this case, which kind of split do we want? Do we want to split an x1 or do we want to split an x2? For example, this is the table that is given to us for a coin flip data. Okay, and then we want to build a decision tree out of it. Okay, so now where do you want to split first? Whether we split first, or that means we want to make x1 as our first layer, or you want to make x2 as our first layer. That is what we call the splitting. Splitting, that means making a decision at a certain layer. Okay, so there are in this case we want to investigate which one will give us a much simpler computation or much simpler tree and a much more uh, predictive case of coming out with a decision, a more a higher possibility of the decision being according to the data that is given. Okay, so now we use to count the leaves to determine the probability of distribution, and so we can measure uncertainty. But anyway, it is about measuring uncertainty and making sure that as we go forward to the layers, we will there will be less and less uncertainty in our prediction. So in this table, it is a coin flip data. What happens here is that we can say that x1 may be the head and x2 is the tail, excuse me, and then the result will be true or false. So we flip the coin where the head, this one, maybe this is not a coin flip data because uh, maybe there are two coins. Yeah, maybe there are two coins where the two yeah, I'm not familiar with what data is this, but anyway, this table is given and we're going to build a decision tree out of this table. What I'm just looking at is that here for x1 you have true or false. Maybe this is, let's just assume that this one is one coin and you flip that coin true or false, true being head and tail being false, and another coin you toss it and then you see true and false, at head being true and tail being false. But then there's peculiar about this data. As you can see, x1 is true and x2 is true. That's true. Then another entry. This is like a redundant entry. True, another true, and this is false. Okay. But the way I interpret it is that we say here this is true or false, true and false, and this is true and false, and that's true. Yeah. That is a redundant information. But one thing peculiar here is here, this one, false and true, and then the output is true, and then false and true, and the output is false. What is your interpretation of the data before we play with it? How come there is such inconsistency in the truth table? And okay, it's done already. There's inconsistency in the truth table, and also there's redundancy in the truth table. Why do you think? Any any guess? Mr. Musa, since you, come on, can you guess what happened there? Why the data is like this? You toss two coins and then the result is like this. Sometimes they're redundant, sometimes they're inconsistent.
If you look at how random X1 was, every time it was tossed, the result was like was true. For four occurrences, it was true. So it kind of repeated.
Okay.
I mean, they expect random systems to have variances.
Okay. Okay. Yeah, that's a good point. Another point. Yes, they're supposed to be random. They're supposed to be random because they're tossing a coin. In this case, I think here x1 being all true and x1 being all false. I think this is not the true sequence. They just take these. Then there was a tossing event, but they just take this. They just give us the data like this in order to make it readable. But the relationship between x1 and x2 and the output y is this. But why? What is the question of it being redundant and it the data being inconsistent? At some point, it is false and true and true, and at some point, false and true and false. Any, I mean, just give me some crazy ideas. Come on.
If it's a coin, there are only
Yeah.
two possibilities.
Yes. But
It's
why?
either it's true or it's false.
True or false?
I
But
mean,
then
if
there's an yes. But then there's an output y.
So what are you asking? Are you asking for the relationship between X1 and X2?
Yes. There's just some strange relationship here. When you have a false and true, okay, false and true for x1 and x2, and you have a y that is true, and false and true for x1 and x2, you have a y that is false. What is your interpretation? And in here, you have true,
okay,
false. Yeah. Yes, go ahead.
those the ones at the top that have that green thing, it is an or, it's an or operation, and the other one is an inverse of an or.
Okay.
Or a no operation is for those red ones, and those green ones are an or operation, because true and true will give you true, true and false will still give you
Okay.
which is just how these systems work, like how the or operation works. And the nor, which is those red ones at the bottom, a false and a false will give you, oh, hey, I don't know now. Yes, still.
But why is the function different for both of them?
Yes. Who's talking? Mr.
Okay.
Tuala. Yes.
I'm asking like why the function is different for for these things. I'm guessing it's one function just defining stuff. So it shouldn't be you shouldn't be getting different results.
I cannot hear properly. Can you make your voice louder?
Oh, I'm guessing it's one function that's defining the output.
Hmm.
So you shouldn't be getting different results depending on the input you're getting. You're getting the same result
Okay.
unless the function is changing through time.
Yeah. Okay. Okay. Let's just continue. What my interpretation is, I don't know it's correct, is that this is a result. I mean, there is some inconsistency. Yes. For example, this one FT, and then the output is true, and then FT, and that output is false. False. This inconsistency of data, I think, is a result of we are not given the entire data set. I think there are other parameters here, for example, time. If you put time there, for example, if you put time there, so then it makes this output unique, you know. Given time, at this particular time, if this is false and true, this is true. Okay, given another time, this particular false, you know, there's just some hidden information that is not given to us. I think because the way it is, it's not possible for us to make such a decision tree without other parameters. Okay, the way I look at it, for example, is like this: you are given a table, yeah, a complete table, but then you just take the first three columns of it. That's my interpretation. But anyway, so whatever it is, let's just use this as an exercise. In a way, we're not going to interpret it yet. It's just for us to exercise on how what will guide us in order to choose a good node for splitting, to choose a layer where we are going to split. So in this case, which one should give us? Should we choose to split whether x1 first at the root node, or x2 first as the root node? Okay. So in this case here, we say if you use x1, okay, When x1 is true, then the output is when x1 is true. So this is x1 is true. Okay, and then all your output are all yeses, are all true. It's four with zero false. Okay, so it's just writing it this way. Okay, and then here, if x1 is false, then you're true. You have one true and three that is false for the y. For x2, if x2 is true, x2 is true, then you have output being true, one, two, three output that is true and one output that is false. And if x2 is true, I mean false, so false, you have true, true, that's one, two, true, and then two, how to say, two, two true and two false. Okay, okay. So I should practice seashells. She sells seashells in the seashore. Okay. Anyway, so so that is, we're just extracting the information. We're just not interpreting the data yet. Okay. So if this is your x1, and so this is the output of the y output, and then x2, this is the y output. So how do we use this information? So the idea is about uncertainty. So good split, a good split is good if you are more certain about the classification after the split. Okay, so we can guide us that we after the split will be more where we are will gives us confidence that we are going towards the final solution, that there are clearer result after the splitting of the node. Okay, how do we know this? So to know this is that if there's the output, the deterministic good, that means everything is after the split, we know everything is true or everything is false. Yeah, that's a good output. Or if the distribution does not help, if after the split we are not able to group the distribution, that means it's still a uniform distribution. That means the data, for example, is still equally distributed. So what we want to do is that we want to have a final result. That means whether everything is false and everything is true. Okay, that's a good split. But otherwise, if in some cases, if after the split the distribution is still good, for example, you have three Asia, three attributes. I mean, what is that attribute? Uh, three branches, Asia, Europe, and America, and all of them have equal numbers. Three, for example, is still uniform distribution. It's not a good, it's not a good split. So what we want to do is we want to find a probability a distribution of the data. For example, in this case, we want it to be as not uniformly distributed as possible. You want it to be as skewed as possible, or as we say as separate as possible. So in this case here, the first case where you have probability of the y output given I mean the y probability of the input of in this case the input is a. So if input is a, then you have one half. And this case, this is a better probability compared to the second case where you have equal distribution. So how do we determine this? Okay, we use the tool called entropy measurement for the distribution of the data of the information. So we say that in this case here, when flipping the coin, for instance, flipping one coin, okay, if the probability of the heads, okay, the lower the entropy, if the entropy is zero, that means you have already, there's no instability. Yeah, there's no uncertainty. It is very certain. Okay, if probability of getting the heads when you're getting a tail, okay, the entropy here is zero. Okay, it is definite that if you don't get a head, you get a tail. Okay, that's the probability of getting ahead. If probability of getting ahead is one, that means definitely you have a head. Okay, the entropy there is zero. Okay, but in between, okay, for example, half probability of getting the head and half probability of getting the tail. That probability, the entropy in between is very high. We are not certain. We are not certain we can get a head or a tail. So what we want to do is we want to avoid this uncertainty. We want to be in this area here where you are certain that you're getting a tail, or this area here you are certain that you are getting a head. Okay. So what this entropy method tells us is that we want to deal first with those cases with higher entropy, with higher uncertainty, so that as we go towards the branches, as we go towards the different layer, our entropy increases and increases until we come out with the final decision of yes or no, for example, or good or bad. Excuse me. So our idea then is therefore, one, we compute this entropy, okay, but we want to choose the entropy that has the highest entropy to be the first layers, or the layer with the higher priority. We take them as our node compared to those attributes, the entropy of the attributes that has the attributes that have lower entropy. Okay. So we based our priority in choosing which attribute we want to make a node first based on the measurement of the entropy. And then what is this entropy? So it is just this equation where you, in this case, y is the output. Okay. There was just, in this case here, y is the input, but, oh, the y is the output. Yeah, y is the output. So in this case here, y being the output. In this case, you have a yes or no, for example. So probability of no multiplied by the log of probability of no minus probability of yes, multiply the log 2 probability of yes. For example, if you have good or bad, and so on. So probability of good, log 2 probability of good minus probability of bad, log 2 of probability of bad. Okay, then it gets clearer as we move along. So there, then just for emphasis, when you have high entropy, you is the Y is from a uniform like distribution. Okay. So if the distribution is uniform, that means we don't know whether you are definitely, there's a definite answer, then that is high entropy. Just like in this case here, there's a higher entropy. We're not very certain about the outcome. Okay. If uniform like distribution, like a flat histogram, or value sample that from less values that are sampled are less predictable. We don't know exactly what's going on from the samples. But low entropy, in this case, there will be peaks and valleys. Okay, where we are we are at the very top. For example, if there are peaks here, if this is a peak, or this is in this case in a valley, if this peak is very very sharp, then we'll know definitely that, you know of course we want to have entropy, lower entropy. But if there are peaks here, okay, then we know that the entropy is very low and there's a certainty. In this case, it's a valley. So I'm going. Hey, where am I? Okay, so we want to deal the histogram as lows and this highs and lows, and various samples are more predictable. So we are going. I have 10 more minutes. So anyway, after this, we will just close the session after when the time runs out. Because anyway, it's going towards finishing time already. So the low entropy is the one with higher predictability. We don't want to deal with them first. We want to deal with those with higher entropy first, because we want to deal with uncertainty first before we deal with those with lesser uncertainty. Okay, it's like, you discipline your students first, that are those that are quite needs disciplining. Those that are disciplined already, they are less priority, because they're less, you know less to take care with. So you take care of those that are uncertain. Okay? You help those students that are needing help, so that the whole class will have better performance at the end of the semester, something like that. And if you're a parent, you deal with students or your children that are more needing more discipline. compared to the other children that are, just following the orders, for the order of the family and also for their future, yeah, something like that. Okay, so uh, let's start. I don't know I have enough time, but I will proceed. Start with the idea of the entropy. I will proceed, and then we'll just finish as time runs out. So we take this table, that is, take half of some portion of the table that was given, this one, until the end. We remove the last two, I think, just for simplicity of information. Again, this is just for exercise. And so now we say that this entropy equation, how do we apply it? So here in this case, you have y, you have two outputs, yeah, x, I mean true and false. So probability of y being true. So how many true? So y, 1, 2, 3, 4, 5. So 5 true out of 6. So that is 5/6. That's the probability. And then being false is 1 out of 6. So that's probability of y being false. That's 1/6. Okay. And so now if you add all those probabilities for the entropy of the y output, okay, entropy of the y output, remember this, the negative sign here, negative of probability being true or probability being yes, multiply lag of 2 of probability of true, again minus, and because this is a summation, minus probability of the y being false, log of y being false. Okay, but if there are many outputs, for example, uh, large, medium, and small, for example. So probability of large, that means in this case, there will be three terms. Yeah, there will be three terms based on the number of outputs. But because our outputs has only two, so in this case, our entropy is computed like this. If it was large, medium, and small, so this will be the term for the probability for the large, minus probability for the small, minus probability for the medium, and minus probability for the small. Yeah, if there were three outputs. But for us, in this example, there are only two outputs, probability of true and probability of false, and thus the entropy is 0.65. Okay, so this is just one measure. There's another measure later that we will discuss in the next meeting. But for now, I want to wrap up by saying that yes, in the case of commutative things like the Boolean decision tree, it doesn't matter which node you will choose. But in more complicated data, we need to choose which node that will help us make the tree to come out with more decisive output. So in this case here, we want to deal with the attribute that has higher entropy first. That will make us our root. The attribute that has the highest entropy will be our root node. And then the next, and we continue as we continue with the next nodes will be the next higher attribute, and so on and so forth. So that as we move on to the layers of the tree, then there's more and more certainty as we move towards the leaves of the decision tree. Okay, any questions? I have 1 more minute left. Okay, I uploaded the lecture slides already in Blackboard, and please work on your laboratory exercises as given as assignment because the TA is still not around. And I will see you next week if you have questions for decision tree. Okay. Okay, just keep your, because we are running out of time, just keep your questions for next week, and then I will answer them next week. Okay, so I will stop sharing now and I will stop recording, and the class is over. Let me